Welcome to this new tutorial for HARFANG 3D in Python. Today we will see how to import and display a 3D scene. We will start by downloading the resources we need, starting with assetc. So for a detailed use of assetc, I refer you to the video which you will find a link in the description below. You can find assetc on the HARFANG 3D website. We will start by downloading assetc. Then we will need the GLTF importer because we will import a scene in GLTF format. I download GLTF importer. Next, we will download the resources needed for the HARFANG renderer. You will find the shaders and textures needed for the rendering pipeline. These resources can be found on GitHub in the HARFANG core repo. I'm downloading in zip format. Finally, we will download the scene we want to display. We will download a scene in GLTF format. The one we use in this tutorial you can find on the GitHub repo in video tutorial resources, in the displacement directory. View row to download it. And we have our scene. Here we have our different resources that I'm going to copy into the project directory. Then we are going to unarchive assetc. We are going to unarchive GLTF importer. We are going to unarchive HARFANG core, which I can unarchive directly here. We will rename HARFANG core to core. We will create the assets directory to put our resources. Let's move the core into the assets. In the assets directory, we'll create a radio telescope directory. This is where we will put the files imported by GLTF importer. Then we will import the scene. For that, we go to the GLTF importer directory. We launch the PowerShell. To know how GLTF works, we can display the help, GLTF importer, and we have here the list of the options we can use. So we'll start by typing the command GLTF importer. We'll specify the output directory, out in assets radio telescope, which is the directory we created earlier. This is where we will place the files of our HARFANG scene. Then we are going to specify the resource directory, that is to say where the core files that we downloaded earlier are. Base resource path, which will be in assets. And finally, we will specify the GLTF file to import. Radio telescope.glb. The conversion has taken place. Then we have a log script to see if everything went well. So we can go to Assets, Radio Telescope, and we see there indeed the files of the scene with the textures, the geometries, and the famous scene file that we will display. Now that all our assets are gathered, we can compile them with assetc so that they can be used under HARFANG 3D. So we open assetc in another window, and we move our assets to the assetc executable, and our assets are compiled automatically. So the process can take a few minutes because in Core, as you can see, there are many shaders to compile. We return to Visual Studio Code to edit our program. So we start by importing HARFANG. Import HARFANG as HG. We initialize the inputs hg.input_init. Then we initialize the window system, window system init. We will create the window res x res y equal 500 by 550. Win equal hg.render init. HARFANG 3D display a scene. This is the title of the window. The resolution we specified just before, res y hg.rf msaa for x for anti-aliasing. Then we are going to initialize what's called the rendering pipeline. So to get information about the HARFANG rendering pipeline, you can go to the HARFANG website under Framework, Documentation, and under Using the Forward Pipeline. There you will find various information about the resources and the use of the HARFANG pipeline. To summarize, the pipeline is the set of resources and processes that allow a 3D engine to calculate and display images. So, we are going to initialize the pipeline, init pipeline. We'll start by defining the resolution of the textures used for the drop shadows. Shadow map resolution equal 4096, this is in pixels. Shadow map 16 bits, this is a boolean. We'll set it to false to optimize the rendering. And we'll create the pipeline. Pipeline equal hg.create forward pipeline. Shadow map resolution. Shadow map 16 bits. Finally, we will create the pipeline resources. It's an object that groups all the resources used by the pipeline. hg.pipeline resources. Then we will add our resources directory, add assets folder, assets compiled. That's it for the pipeline. Then we will load the scene. So load scene. First, to create the object scene, scene equal hg.scene simply. And then we use the function load scene from assets. It will fetch the file in the directory we specified with the add assets folder function. So radio telescope scene.scn. This is the file we created earlier using GLTF importer. We specify the scene object, the pipeline resources, and hg.getForward pipeline info. This function is simply used to collect information for the HARFANG loader. So, once the scene is loaded, as it is a scene that we have just imported and that is raw, it has no camera or lighting, so we will add what is missing to make the scene presentable. We will start by creating a camera. Compose equal hg.vex3 9.31 in x, 2.72 in y, 12.99 in z. We will give it a rotation. Camrot equal hg-3 minus 7.6 degrees in x, minus 143 degrees in y. And we create the camera. Cam equal hg.create camera. We give it the scene. We create the matrix of the camera. Transformation mat4, compose camrot. We will define the z near of the camera on the z far of the camera at 2000, the closest point on the farthest point that the camera will be able to display. Then we give it the opening angle, deg 40 degrees of opening. Then we define this camera as the camera currently used by the scene. Set camera, set current camera cam. Then we will define different display parameters of the scene. Set scene environment. First, the background color, which is accessible in the canvas. Scene.canvas.color equal ag.color_i. We will define the color thanks to integers from 0 to 255, 88 in red, 151 in grid level, 206 in blue level. Then we will define the color of the fog. We will activate the fog. Scene.environment.fog color equal hg.color_i 12, 23, 45. Then the distance where the fog starts, environment.fog near. The fog will start from 10 meters, and fog far. The fog will be at its maximum at 18 meters from the camera. And then we will create a light source. LGT equal hg.create linear light. It creates a linear light whose rays are parallel at all points to simulate the sun. hg.transformation mat4. So for a linear light, the position does not matter, so we put 0. It is the orientation that counts. Deg3 45 degrees in x, 120 degrees in y, 0 degrees in z. Then we will define the color of diffusion, hg.color.white. It will be a white light. The intensity of the diffusion component to 4. Then we'll define the specular color, hg.color.white. Intensity always at 4. The priority of the light source. We will come back to the priority of light sources in a future tutorial. Here we will set it to 10. Then the type of shading generated by the light source. LST light shadow type map. So the light source will use textures with a resolution of 4096 to generate the shadows. Then what we call the shadow bias. the shadow bias, which is a parameter of fine adjustment of the start of the shadows. Next, we will define the PSSM, so the PSSM for parallel split shadow mapping. In fact, to optimize the resolution of the drop shadows, we generate them in 4 different textures. The closest texture will be generated on a small surface, which will make that the shadows close to the camera will have a high precision, and the shadows farthest from the camera will be generated on a large surface. They have a low precision, but as they are far, this low precision is much less visible. And so what we will specify for our light source are the split distances. The first drop shadow texture will go to split distance 1, the second to split distance 2, the third to split distance 3, and the furthest away to split distance 4. So, the greater the depth of field of the scene, the more we will need to distribute the drop shadow textures over the distant split distances. Our scene doesn't have a very large depth of field, so we're going to define fairly close split distances. So we put this in a vec4, hg.vec4. 1 meter for the split distance of the most precise shadows, 5 meters, 10 and 20. Then we will create our main loop. Main loop. We will wait for the user to press the escape key to exit our program, while not hg.read keyboard dot khg dot k escape. Then we will get the delta t. The scene needs it for its update. hg.tick clock returns the delta t between each frame. Scene.update dt. This function will allow HARFANG to calculate the matrices of the different objects making up the scene. And finally, we will send the scene to the rendering pipeline. Submit scene to pipeline. We'll send it to view number 0. For the concept of view, I refer you to the tutorial HARFANG First Steps. You will find a link in the description. We give him the scene. We define the rectangle in which this scene will be displayed in the view. It will occupy the whole view, res x, res y. The next parameter determines the axis on which the opening angle we define here extends, the opening angle of the camera. We will set this to true to tell it that this axis extends on the horizontal axis. So we are in a square window, so it doesn't matter much. But this parameter will be important if we were working in a rectangular window. We give it the pipeline that we have created here and pipeline resources that we have created above and that contains the different objects and textures of the scene. Then we will generate the frame, hg.frame, and we will update the window, hg.updateWindow, win. And finally, don't forget to disable the renderer, hg.render shutdown. When we quit the program and destroy the window, hg.destroyWindow, win. We can now launch the program. And we have our scene, which is displayed our radio telescope. So now we are going to add some animation by making the camera rotate around our scene. To do this, we will first create an empty node. Create empty node. Empty node equal scene.create node empty node. Then we will add a matrix to this empty node that we have just created. Empty node dot set transform send dot create transform. The matrix of a node is in a transform object, and when we create this transform object without specifying either the position or the orientation, these values are set to 0. So we will have a node located at the origin of our space. Then we will define this empty node as parent of our camera. Cam.getTransform dot set parent empty node. In this way, we will simply have to rotate our empty node on its y-axis so that it is the camera that rotates around the scene. Then we will create our variable that will allow us to rotate the camera. Angle plus equal hg.time to sec f dt. We transform our delta t, which is in nanoseconds, into seconds, and we'll multiply by 10 so that the rotation isn't too slow. And finally, we will rotate our empty node, which is the parent of the camera. Empty node dot get transform dot set rot hg.deg 3 0 on the x-axis, our angle on the y-axis, and 0 on the z-axis. We run the program, and here is our scene which turns. And that's it. This tutorial is now over. You can subscribe and activate the bell to flatter the YouTube algorithm. See you soon for a new tutorial.